Today we're going to be talking about graphing the standard form. So this is the first part of that. And so for our warm-up today, we're going to look at matching graphs to linear equations. So if we look at graphs A, B, and C, they represent three linear equations. One of them is y equals 2x plus 4. Another one is y equals 3 minus x. The last one is y equals 3x minus 2. And we need to figure out which graph corresponds to which equation and explain our reasoning. So we have y equals 2x plus 4. We have y equals 3 minus x. And we have y equals 3x, which that should be a minus 2. Okay, so we have those three equations, and then we have line A, B, and C. So what things do we know about these from when we graphed them in the past? What two things would you need to know? You need to know the slope and the y-intercept. So if we're looking at this, the if we're looking at y equals 2x plus 4, the slope of that is 2 over 1, and the b, the y-intercept, is a positive 4. For y equals 3 minus x, okay, remember m is always the number that's in front of the x, so even though it seems out of order, our slope here would be negative 1 over 1, and our y-intercept would be the positive 3 that's there. And for this last equation over here, our m is 3 over 1, and our b, our y-intercept, is a negative 2. So the easiest thing to find out of all of these is the y-intercept. So we have a positive 4, a positive 3, and a negative 2. So if we're looking, obviously the negative 2, that being the only negative thing, is the easiest one to find. Well, along here, that means that negative 2 is this, and it does have a positive slope. It is going uphill, so that would be graph C. Between these two ones, we need to have a y-intercept of 4 or a y-intercept of 3. So the higher one would have a y-intercept of 4. It also has a positive slope since it's going uphill. That means that B is the 2x plus 4. And just to make sure, so this starts at 3, it's lower than that 4, and it does have a negative slope. It's going downhill. So then this would be graph A. All right. So next we're going to have quadratics graphs galore. So using graphing technology, we're going to graph y equals x squared. Then experiment with each of the following changes to the function. We're going to record our observations and what we notice. Okay, so the first thing we're going to do is look at if we add different constant terms to x squared. So if we look here, okay, I have taken x squared and graphed it, so I'll show you here. I have x squared graphed. The blue function is x squared plus 5. The green function is x squared plus 10. And the purple function is x squared minus 3. So what happens to these when we're looking? So here's black, the original. What happens to these? As you add 5, so that's the blue one. As you add 10, that's the green one. And as you subtract 3, that's the purple one here. So with this, as you're adding a number onto the end of it, when you're adding a number, what happened to those? So just shifted it up that many spaces. When you're subtracting a number from it, that's where it's going to move it down. Did it change how wide or how skinny it was? No, it's the exact same thing, just shifted up or down. Okay, so adding different constant terms is just going to move it up or down. So adding moves up. We'll say k spaces. Okay, k being this number that you're adding, and subtract means it's gonna move it down k spaces. Okay. So then what happens if we multiply x squared by different positive coefficients? Okay, and these positive coefficients need to be greater than 1. So if we're looking at these different pieces, So again, I've gone ahead and graphed them. So let me get rid of these other ones. We don't need those anymore. So we have x squared, that's the black. 3x squared that they've given us as a suggestion is the red, and 7.5x squared is the green. So let me get rid of this so we can see it maybe a little bit clearer. So what happens? Here's your original. When we multiply by 3, we're getting a little skinnier. When we multiply by 7.5, we're getting even skinnier again. Okay? So what's happening here? So multiplying by a positive number. So let me move our graph out of the way. Makes the graph steeper, or you could say skinnier. So the bigger the number, the steeper or the skinnier it's going to get. Okay? So it is going to make the graph skinnier. All right, so let me get the next set up here. So what happens if we multiply x squared by the different negative coefficients that are less than 1? So again, we have our functions typed in here. The original, the parent function, y equals x squared, is in black. Y equals negative x squared is in blue. And y equals negative 4x squared is in red. So I'm going to get rid of those. Okay, and as we're looking at this, what's happening? What do you notice? Well, if we look at the original, and then we look at x squared, negative x squared, those are the same width. They're both the same width here, but what happened to the graph? Yeah, reflected across the x-axis, okay? So multiplying by a negative makes it flip over, okay? So multiplying by a negative number flips the graph downward. Okay, all of our other ones looked like they were going uphill, or they were facing up. It was a U facing up. So now that we have a negative in front of them, both of them face down. Why does it make sense that the red one, remember, the red was negative 4x squared. Why does it make sense that that one is skinnier? Well, that's because of the whole idea of multiplying by a number that's bigger than 1. So the negative part is what flips it over. The 4 is what makes it be skinnier than the original. Okay? One last set to look at with this. We're going to look what happens if we multiply x squared by different coefficients between negative 1 and positive 1. Okay, so if we have this, they've given us some examples. So our original is still in black, y equals x squared. We have y equals 1/2 x squared, which is the green. And then we have y equals negative 25/100 x squared. That's going to be the purple. Okay? So if we're looking at these, what happens when you're multiplying by a number between -1 and +1? So with this, let's focus on the ones higher up here first. Here's your original, and this was 1/2 x squared. What happened to that? So it got a little wider, okay? Or you could say that it got shallower as this happens, if it's a number that's between 0 and 1. So multiplying by a number, let's see, let me get rid of this for a second, number between 0 and 1 will make the graph wider, or you could say shallower. What happened to the one that was negative 0.25x squared. So that one faced down. Why do you think it faced down? Well, because it was negative. This 25 hundredths as a fraction would be 1/4. Is that, so ignoring the negative part, is that bigger or smaller than the 1/2 that we already had? So 1/4 is smaller than 1/2. That's why this one, the negative 25 hundredths or the negative 1/4 x squared is wider than the 1/2 x squared. The 1/2 x squared is going up because it's positive. Okay, so then we're going to say multiplying by a number between -1 and 0 will make the graph wider and flip downward. Okay, what happens if we multiply by 0? So if we have 0x squared, okay, and let me change the color of this really quick. So if we multiply by 0x squared, I'm going to zoom in a little bit here. You're going to notice that it's just the x-axis. So that's just a horizontal line. Well, that makes sense because if you're multiplying something by 0, it's just going to be 0, and it would not need any sort of shape to it. Okay? So the other thing we're going to talk about here is, what do these tables reveal? So we're going to, well, I've already worked on completing the table with these values. So they gave us x and x squared. So you just take each of those x values and you square them to get this. And then this is asking us to take x squared and add 10 to it. So if you're looking at each of these things, you've just added 10. And x squared minus 3 means we're going to take our x squared answers and we're going to subtract 3 from them there. So that shows you in a tabular form that adding a number is literally adding that number onto all of your answers from when you had the original parent function of x squared. And when you're subtracting a number, you're actually just subtracting that from the x squared as well. Okay, so that's what happens in that table. In this table, we're looking at all of those values where we have x and x squared again, that's our parent function. So then what happens if we multiply by 2 out front? Well, we're going to take our x squared and multiply it by 2. So every single term here has just gotten multiplied by 2. It's 2 times bigger. That's why it gets skinnier. Okay. Here, if we have x squared and we go to 1/2 x squared, what do you notice between all of these values? So each one has gotten a half as big as it was before. That's why it gets wider as it goes. And -2x squared, so we're multiplying by a negative number, and then that number here, again ignoring the negative, is bigger than 1. That means that it's going to multiply that actually by -2 each time. So all of these are multiplied by -2, and that's going to make it flip over the x-axis. And it's also going to make it skinnier, 2 times skinnier to be exact. So things to keep in mind, okay, when we have these things, adding a number, a constant after the x squared is going to move it up that number of spaces. Subtracting a number after the x squared is going to make it move down that number of spaces. If you multiply by a number that's greater than 1, that means that it's going to get steeper or skinnier. Okay. If we multiply by a negative number, then that's going to flip it over. Okay. It still could make it skinnier if that number is not just -1. And then if you multiply by a fraction, it's going to make it wider. If it's a negative fraction, it's going to flip it down and make it wider. And that's it.